The Institute for Shock Physics at Washington State University is a multidisciplinary research organization with the primary motivation of doing experimental research and analysis on understanding how materials behave under extreme thermodynamic conditions. We use the term shock physics and dynamic compression quite interchangeably, but effectively what we do in this work is we subject materials to extreme thermodynamic conditions, meaning very high pressures, very high temperatures, on a very short time scale. What is unique about the shock physics program here, or research program here, is it's extremely broad. We do physics, we do chemistry, we do mechanical engineering, we do material science, we do geoplanetary science. There is no other program that even comes close. And students from different departments come and do their research here. And they come and study how materials of interest to them in these different fields behave when they're subjected to very high pressure shock waves.
The Institute for Shock Physics is unique, not just as an academic institution, but also as a shockwave research facility because of the wide variety of tools that we have for doing dynamic compression research. In the laser shock facility, we generate shock waves by using a laser pulse. And if the laser pulse is tightly focused, we can reach very high pressures. In the impact laboratory, we shoot a projectile into a target and we watch how the material responds in real time as the shock wave passes through. The Institute also has static high pressure capabilities. In these experiments, the sample is loaded between two diamond anvils that apply a nearly constant pressure. This offers the ability to compare the dynamic response of a material driven by a shock wave to the static high pressure response of the same material compressed between diamond anvils.
The Dynamic Compression Sector is a national user facility located at the Advanced Photon Source at Argonne National Laboratory. Washington State University runs this facility for the Department of Energy Defense Programs, and it's truly a unique facility, the first of its kind worldwide. Our impact facilities are much like the ones you see behind me, where we can generate impact velocities up to 6 kilometers per second, which is about 13,000 miles per hour or 20,000 feet per second. WSU has a long-standing history of shock compression science, really pioneers in this field academically.
WSU students and faculty members have played a pioneering role in developing and using time-resolved multi-scale measurements in shockwave experiments.
Shockwave experiments generate a unique set of conditions by rapidly compressing, heating, and deforming material by subjecting a sample to an impulsive load. The excitement and the challenge is that these destructive experiments last a millionth of a second, and we need to make real-time measurements with picosecond to nanosecond resolution. It's amazing the complexity of behavior materials can exhibit when subjected to a shockwave. Each material is unique. Some will go through a phase transition by melting, freezing, or solid-solid phase transition. Other systems may go through a chemical reaction, like polymerization in a liquid or decomposition of energetic materials. Most commonly, systems will deform and fracture, but in ways that are not only unique to the material, but vary by the direction we apply the shock wave. The goal of the Institute for Shock Physics is to have students take intellectual ownership of their work. Students have the responsibility of sample preparation, sample metrology, and running their own diagnostics.
I was really interested in the research that they do here, but also the student experience. So the facilities available to students, the hands-on training and learning that we do here, and the availability of opportunities here is something you can't really get at any other university. My PhD research project is on melting of aluminum single crystals under shock compression. So specifically, we want to study how different orientations of aluminum single crystals melt differently under shock compression. Recent work has shown that even though different orientations of the crystals have the same material response, the sound speed in the crystals are different along different orientations.
I chose to do research in shock physics because the hands-on, experimental material science research matched my interests well. In 1961, cubic diamond was first recovered from an explosively driven graphite sample. Since then, a lot of research has been done on the shock-induced graphite to diamond phase transformation, but there are still some questions that remain unanswered. So my PhD research involves trying to better understand how different graphite microstructures affect this shock-induced graphite to diamond phase transformation. I use the two-stage gun to achieve projectile velocities around 7 kilometers per second. The projectile then impacts the target, which has my graphite sample in it, and drive shock waves into it. We probe the particle velocities at the rear surface using VISAR and PDV velocity interferometry systems. By making these measurements, we're able to determine the transformation stresses and the in-material states.
In shockwave research, we're always stumbling upon things that are unexpected. Because of the extreme states that we generate and the very short timescales that we generate them on, we're always finding new things that were unexpected and pushing our understanding in new directions.
It's the ultimate intellectual adventure. Come prepared with passion, creative ideas, be ready for hard work, and don't accept conventional wisdom. Always be prepared to disagree with conventional wisdom. That's how you'll do great things here.